And originally this was just called Snakes on a Car. But halfway through giving this talk at the world's first tech conference in Animal Crossing, I realized that what I had done was over-engineer the hell out of a toy for work. I got paid for it. So, you know, that's always a pretty sweet thing to have, getting paid to have fun. So a little bit about myself first. My name is Kat Cosgrove, and before I was a developer advocate, I spent about a year on our IoT team here at JFrog. We built a very flashy, somewhat ridiculous, complicated demo proving that software updates for cars don't have to be as complicated as they are. Currently, it is a huge inconvenience. Most cars can't update over the air. Some of you are probably thinking, oh, but Teslas, yes, Teslas can, but they are like far and away the exception to the rule. For most cars, even very expensive ones, an update to one of the 5 or 6 computers running in there has to be done by taking the car into a service center. The only like real update strategy for a car is generally it's just flashing it. They just get reflashed. A really good example of this is the Jaguar I-Pace, which is a very beautiful but very expensive luxury car that had a problem with a computer that handled the brakes. It was causing a failure of the regenerative braking system, and the solution was reflash the computer. They had to issue a widespread recall for the car over a software problem, and that sucks. It's expensive and it's embarrassing and it's wildly inconvenient for the user. So we built a proof of concept that showed that you didn't have to actually do it that way. Sorry, she's screaming. I have a whole technical talk on how this demo actually worked, but what it boils down to is we allowed updates in one of 2 ways, app level updates on the car or a full firmware update. And we managed to get to doing either of those things without actually interrupting the user, at least not in a noticeable way. An application update to the car could happen within like 35 seconds, and a full firmware update took about 5 to 10 minutes without interrupting the user. And this relied on K3S, Yocto, Mender, JFrog Artifactory, and Helm, and it was glued together with a whole bunch of Python. It was very cool, it was very impressive, but the technical talk on that doesn't include my favorite part about that proof of concept, which was making a miniature self-driving car, because obviously JFrog was not going to buy me a whole car for my team to potentially brick. That would be ridiculous. So instead, we had to build one, and this is how you can do the same. If you would like to get a hold of me later, I am on Twitter at Dixie3Flatline, and my slide deck, as well as all of the resources I mentioned in this talk, will be up at jfrog.com/show notes afterwards. They might actually already be there, I'm not sure. Anyway, so what is this demo? That's mostly what I have already gone over, but it is less... I'm not going to say it was less difficult than you would expect to make that happen, because it definitely wasn't easy. But what's important is we proved that the tools already exist to make this a solved problem. There are obviously a ton of other hurdles that we didn't run into that car manufacturers going to run into. Regulatory problems, issues of like not having standardized hardware, whereas we were working with things that are available off the shelf, and embedded Linux development is not actually as easy as we made it look in this proof of concept, but it was flashy. It also looked really flashy. It was ridiculous, actually. So we had this racing simulator set up in the middle of a large track, complete with pedals, wheels, and a screen that's showing the camera feed from the car. We bought like almost an entire racing simulator setup. It was a little bit ridiculous. Marketing really wanted it to look as flashy as it was from a technical perspective, so they let us go a little bit nuts on it. This is just me making sure everything is set up before the conference opened. I wouldn't actually recommend trying to like drive and write code at the same time. I mean, I didn't crash it, so maybe go for it if it's a tiny car. But we were writing and pushing updates to the car while it was driving. I know that live coding demos are always risky, but we were extremely confident in what we wrote and the safety nets we had in place. So we actually did let like real random people off of the conference center floor stand up here and write code and push it to the car. So you could interact with it in one of two ways: as a developer pushing code, or as a driver driving the car around while somebody else made changes to it. Usually we found we got teammates for that, and the marketing guy or the sales guy or somebody from biz dev, someone non-technical, wanted to write the code, and the developer wanted to drive the car. And almost always the non-technical person at the computer wanted to push an update that would degrade the driving experience. We did allow them to push updates that like made the steering wheel super sloppy or whatever, but it was really fun. It was really cool. And you can build one too and use it to harass your friends, roommates, pets, partners, whatever. I use mine to harass my cats. They love it. Well, I mean, they love the thing I tie to the back of it and drag around the apartment. So it's worth doing yourself. So let's talk about the basic car first. This began its life as something that's called a donkey car. They are pretty fun on their own, and they're also fairly accessible for a lot of people. They cost about $250 in parts. If you aren't super familiar with these, I very much was not before I heard of them at a different Python meetup. Actually, it's just a miniature RC car that's been modified with a Raspberry Pi and a little camera. The library that lets it do its thing is called Donkey, hence the name Donkey Car. I'm not sure why they called the library Donkey, but it is what it is. In its most basic form, you can build one for like $250. It's not bad. Couple hours of your time max. And we will also raffle off a kit of all of the parts for one later. There's like on the show notes page, there's a link to the raffle if you want to try it for yourself. But once everything is set up, you record 10 laps or so on a like really high contrast track. Even like white printer paper on the floor will do it. But we use like colored masking tape most of the time. 10 laps or so. Then take the images and the steering data from the Raspberry Pi on the car, dump it back to your computer, train the model there. The Donkey CLI handles all of this heavy lifting for you. You don't actually need to know much about machine learning to do it. And then send the model back to the car, turn it on, and let her rip. And 10 laps is enough if it's a high contrast enough track and it's not very complicated for it to mostly go at fairly low speeds without crashing. If you want it to drive more accurately than that, it does take a lot more time to train this thing effectively, but it's really pretty low effort. And it's a good way to dip your toes into hardware if you're not quite comfortable with messing around with boards. Some people are not, and that's fine. But it's a good way to learn. So a whole community exists for modifying and racing these things. People will put the standard is just a Raspberry Pi cam. Like they're like $10 or something, and they're not great. They're serviceable. but some people will put like a second camera on it for stereo vision, or a LiDAR camera for better depth perception. It's also fairly common to swap out the wheels on them or to chuck a bigger battery on it. Ours was pretty close to a stock donkey car. We did build like the more expensive version of the stock donkey car, but the only modification we made beyond that was, instead of using a Raspberry 3B, we use a 3B Plus with a compute module, because we knew we were going to need to try to run Kubernetes on this thing. And a regular 3B Plus is, I think, probably not going to cut it. So I'm kind of extra, and we wanted a setup where it felt like the person participating in the demo was actually playing like a racing sim game. And we couldn't exactly 100% duplicate that experience, but I feel like we got pretty close. It meant that we would need to have the driver have the ability to control the remote car with an actual wheel and pedals, because by default, Donkey wants to be controlled with like a web app on your phone, and it's not the most engaging experience. We would also need the camera feed from the car's camera on a screen in front of them so that the driver knew when to turn and could actually see well. And even then, it's still a little bit disorienting. We also didn't want to deal with having to stop the car, take the cover off, unplug the LiPo battery that is powering the car itself, move the training data to a computer, wait for it to train, move it back. We needed to automate that. And because things weren't already complicated enough, we'll add a green screen so that people have something nice to look at. I regret the last one a little bit still. So let's talk about the controls first. Like I said, it wants to be controlled with a web app on your phone by default. It's not very interactive. It does work really well, but you're sitting there like this, and it's not the greatest experience. It doesn't give us the driving feeling we want. So the library calls its various moving pieces parts, and it's got support baked in for swapping in custom parts. There actually was already a part available for a like Logitech external USB race wheel, but it didn't work with the specific model we had. That was our bad. We should have checked for the specific models it supported. We assumed incorrectly that they all kind of would show up mostly the same as far as the computer was concerned, and that is not true. So as of the version of Donkey that's like 9 months old, the built-in race wheel part does not work with a Logitech G29 driving force. I think it works with the 27 and the 28, but not the 29. So we had to write our own race wheel part, and in the process of doing that, we actually simplified it a lot. The standard parts they had for swapping out third-party controllers were more complicated than I would write Python, but I don't know, they worked, just a little bit more complex than I would do it. So this is what we ended up with. The race wheel part just requires ZMQ and PyZMQ, and it works by requesting values from the race wheel and pedals via a ZMQ proxy running on an Intel NUC the race wheel is plugged into that is hidden underneath the driver's seat. And there's just a script running on the NUC running like evdev to watch for input events from the race wheel. And actually a whole lot of this demo ran because of that ZMQ proxy. This was how I learned 0MQ, and I think I'm in love with it, actually. But this is just a snippet of the wheel object. It's the most interesting pieces of the wheel object. It does also have methods for running threaded and polling for updates, but that's too much code for a slide deck. So this is the snippet you get. But if you want the whole thing, just like message me and I'm happy to give you the code. And most of the other modifications I made for this, I'm happy to just hand over if you want to get weird with your donkey car as well. So once the part is added, swapping it out is just, it's a one-liner. You SSH into the Raspberry Pi that's on your car and open up manage.py. There's just a default joystick controller object. Swap it out for this, and you're all good. To make the steering feel a little bit more like an actual car, we did have to do some processing on the values from the race wheel before they get sent to the car. The standard donkey library doesn't really account for things like throttle scale or steering veer, so we have these two little helper functions doing that math for us before sending the values to the car. Otherwise, the throttle feels really awkward. Like it's very touchy. It is 0 or full blast, and that's pretty much it. And the wheel is like, I don't know, it feels sloppy. This also does play into letting us change the force feedback on the controller. The Logitech G29 has like artificial force feedback, so you can determine how easy or hard it is to change or to turn the wheel, which is really cool because people have different preferences about that, it turns out. Without this, driving the car with the wheel and pedals is totally doable. It's just kind of disorienting. It doesn't feel natural at all. So on the driver's seat, the track is circular, so for that reason alone, we need the camera feed from the car. The driver needs to be able to see what the car is seeing, or they are going to crash into the wall every time they drive behind the driver or directly in front of the driver. It's also really, really fun, by the way, once you have the camera feed to use this, I guess once we get back into normal offices. In my office, we use this frequently when somebody is ignoring us on Slack on the other side of the office. We'll drive the car over there and bang it into their door repeatedly. And that usually gets the message across. But this is what the driver's seat relied on. What we ended up with is a Sanic web server doing most of the heavy lifting for the back end and a Vue.js app for the front end. Instead of storing all the training data in a directory on the Raspberry Pi, which is how Donkey wants to behave naturally, we reroute each frame and the associated steering and throttle data through the ZMQ proxy under another topic. And then we just have an async function subscribing to that topic, as well as a couple of others that handle things like our CI/CD pipeline. And according to whatever the current customization settings are in the config file, it just processes the data. At the bare minimum, the Vue.js app on the driver's screen displays the raw camera data from the car, the number of artifacts, the current build, vulnerabilities, build time, and the current version of the self-driving that you are running on. I will not show the code for the Vue.js app at any point in this because it is frankly some of the ugliest JavaScript I have ever written, and it was never meant to see the light of day, and it's going to stay that way. Sorry if anybody was super interested in a crappy 4-hour Vue.js front end, but the way this worked was by using the JavaScript OpenCV bindings, which is the thing that exists. Didn't know that. And just an open WebSocket to continually rewrite the frame over a canvas element. It's pretty simple, but the JavaScript OpenCV bindings do take forever to load in. So at this point, the car functions the way we want it to, but it doesn't look as cool as it could. The driver doesn't have any nice scenery to look at. You're going to be looking at everybody's feet. And not only might that be distracting or gross to some people, it's also super distracting to the self-driving. We found that if we didn't minimize unpredictable things like people walking around or not walking around when recording laps. It was very hard to get a self-driving model that actually worked consistently and didn't crash into walls all the time. So let's throw some green cardboard around the track and write a green screen. I will admit that this was not part of the original plan for the proof of concept. It was not a thing. This was feature creep from an executive who thought it sounded cool. We were originally just going to stand up like black poster board to eliminate the distraction element. I was very new at the time and riddled with imposter syndrome and absolutely desperate to impress my boss. So of course I was like, yeah, I can totally do that. Like, no problem. I definitely know how to do that. And I did not know how to do that. So I had to learn as I went. Anyway, it worked. And this is how you do that.
Could we ask a question?
Yes.
How did the SANIC work out? Does it require special libraries for async, for SQL Alchemy, etc.?
So there was no SQL Alchemy involved in this at all. There was no database interaction, but the async function was on the side of the JavaScript, not on the side of the Python. But we did briefly try this a different way using Tornado, I think. There's a Tornado that has Asyncio packaged in, I think.
Yeah, Tornado is all async.
Yeah. We tried it with Tornado first, and it was just not fast enough because that's also why we were using 0MQ and not just like a REST API when the driver is relying on the input from the camera on the car to be able to tell when to turn. Latency really, really, really matters. And we found that if we had a latency greater than like 200 milliseconds or so, it was extremely hard to drive the car around a tight track. If you had like a lot of space and you could afford to be a little bit late turning, it wasn't a problem. But driving a circular track, 200 or 300 milliseconds was enough latency to make it effectively undrivable. So that's why like speed was paramount. I had never used SANIC before. That was a recommendation from my tech lead. Originally, I built it with a Flask server. But does that answer your question?
Yes, thank you.
Sweet. So onto the green screen. In its simplest form, script like this works by using OpenCV to read in a frame, convert it from RGB to HSV, and create a mask out of any parts of the image that fall within a range of HSV values you define. It can be a little bit hard to like fine tune that high and low range for your HSV, and lighting does affect it. So we kind of like fudged it in the office, and once we got to the conference center, fine tuned it there because the lighting was like radically different. But there's some fuzzing you can do. It's not hyper sensitive, but it is a little bit touchy. You then use that mask to crop out the background image you want and replace the corresponding spaces in the original image. And to get the edges a little bit closer to perfect and also compensate from your maybe not perfect high and low range, you can run an erode and dilate a couple of times to kind of blur things out, get it closer to perfect. We never got it super perfect, but it was good enough, you know? Then you just have to convert it back to RGB and return it. I have to return it as a string here because I'm doing some additional processing on it later, but in general, at that point, you're okay to just convert back to RGB and give it back. But our green screen needs to simulate scenery on a drive. So we couldn't just leave it static. The image needs to appear to move as you're driving past it. Otherwise, it is crazy disorienting, and even like being aware of it and consciously thinking about the fact that like watch the floor or whatever, it's really easy to crash. So we had to fix that. And the solution was to use the current angle of the steering wheel and starting X and Y coordinates to calculate how far we needed to move the area to crop for the background from one frame to the next. And this is how we did that. We also had this scale variable here to increase or decrease the speed of the pan and make it feel like you were going faster or slower. We didn't actually mess with it much because that was also really easy to change in a way that radically degrades the driving experience. We did also allow for updates to be pushed in the form of like changing the background on the green screen from like the desert to the countryside to driving straight through Puget Sound or space or whatever. We also allowed things like inverting the colors or flipping it so that the green screen was on the ceiling. The last two also really, really disorienting updates that people loved pushing just to mess with their friends. So people are mean. That's what we learned out of that proof of concept. Not updating cars is hard. We learned that people are really mean to their friends. Automating the training. In its current state, the update looks like this. If you want to train a new model, you need to stop the car. You need to plug the Raspberry Pi on the car into the laptop, which means you need to take this big honking cover off of it, which is kind of a pain. Plug the Pi into the car. Manually move over the images and the steering data. Wait like up to an hour to train a new model on a MacBook Pro. If it's a lot of laps, it can be extremely time consuming. So wait an hour, then manually move the model back to the car and reboot it. That sucks. So we needed to automate that. This was actually really low effort relative to everything else we did. It was probably the most impactful as far as like quality of life goes, but it was almost completely painless, honestly. Once we got over some hurdles related to TensorFlow on GCP, at least. So we moved all of this training up to GCP since we're already getting the images and the corresponding steering data from the car via our ZMQ proxy, because remember, we're already using that data in two different places at this point. We just passed the data along to this TubWriter utility we found on GitHub that is also running on the NUC to collate the data and then pass it up to GCP to train the model there. This should be just included in Donkey as an option, I think, because it is such a huge quality of life improvement. I wish there was like part support for routing everything through a ZMQ proxy. Maybe I'll just issue a pull request for that, because it made this so much easier to deal with once we'd added it. So once a new model is available, the driver's UI just updates to let them know that there's a new version of the model available. And if they want, they can select that and it'll go. This is still pretty time consuming, but it's time consuming in a way that doesn't impact the driver, and it didn't impact myself and my two teammates trying to run this booth at a conference all by ourselves. It takes 10, 15 minutes to train a new model every single time, but that's way faster than potentially up to an hour doing it on one of our own laptops, and it doesn't involve taking one of the cars offline, because we only had the two. If they can see my camera, I can actually show one of the cars, because I have one here.
Yeah, everyone can see the camera.
Sweet. Let me mute this because it's really loud. So this is what one of the like fancy ones looks like. This is maybe like $70 more expensive than the stock donkey car, and the only difference really is that the car we started with, like the base model car, is much larger, so it steers better. But it's just, this mounting frame comes from the Donkey Shop. This is 3D printed, so if you have a 3D printer and you want to build one of these, they will just provide you with the STL files, and you can print the parts yourself, which I think is really cool. If my office had a 3D printer at the time, I would have done that, but we didn't. We do now. So otherwise, that's it. Like, the only thing that's beefier about this one is that instead of just a Raspberry Pi, it's a compute module, and it would work the same. Like, all of these modifications can be made to a standard donkey car without the compute module. We only needed this for the update portion because we were not going to get Kubernetes to run on a normal Raspberry Pi, you know? K3S is cool, but it's not like that cool, you know? So that's what the car itself looks like. And that's how the fun parts of this demo worked. It's not revolutionary from a technical perspective, but it is really, really fun to build, and it's a great opportunity to teach yourself about hardware and computer vision and a little bit of machine learning, messaging queues, all stuff that I had never really touched before I did this in the course of my job, and all in one project. Personally, I did a lot of learning while I was doing this, like as an engineer and as an employee, learning to set boundaries with management when they feature creep you 3 weeks before your deadline. I can't publish all of the code for this, but I can publish all of the code I've shown you. So if you're interested in building one of these and you want to make some of the same modifications I did, but you don't want to reinvent the wheel, please hit me up, and I will be more than happy to provide you with the racewheel part, or the green screen, or the ZMQ proxy and everything that went into making that work. It'll make your life a little bit easier, so you don't have to start from scratch. And I would love it if you improved upon what I did. So if you try to do this and you have questions, please reach out to me.
We have a question now, actually.
Hit me.
So Rory would like to ask, how long did the whole thing take to build and code?
The whole proof of concept took 3 engineers about 6 months. The donkey car itself, one person could build that in a few hours. With figuring out the modifications we made, if you had to like do that from scratch, I would probably take you another week, maybe. I did a lot of this alone. This was the part of the demo that got relegated to me. And there were a lot of very cool features that did not, unfortunately, make it into the final that I spent a lot of time on but got thrown away. But if you just wanted to make these modifications, a week, a few days, probably. Depends on how much experience you have with Python, I guess.
Great. Chris has a question. What features did the team want to develop that didn't make the cut?
All right. We wanted like so badly to track how the car improved its ability to drive itself over time. Not for it didn't have any like real measurable impact on like sales or whatever. It wasn't a marketing stunt for us. We just wanted to see that data. So we had this like crackpot idea about putting scaffolding over the booth and hanging a camera in the middle of it so it could watch the car. And we built this out in the office. Initially, we used a visible light camera, we used a fisheye Raspberry Pi camera, but it's not high resolution enough, and there's too much going on, and we couldn't get it to consistently identify the car and follow it around on a camera that crappy from that high up. So what we ended up with is a Raspberry Pi Noir, which is an infrared Raspberry Pi camera, and an infrared LED on the back of the car. And apparently, if you crack open a floppy disk, the actual like floppy disk itself, that functions as an infrared filter. So if you tape that over an infrared camera, it will now only see infrared light instead of infrared and visible spectrum. So from there, we just had to have it watch for a white dot, like find the white dot and follow it around and track how frequently it deviates from the median. And I really wish that had made it into the proof of concept, because it's by far like the hackiest thing I've ever done, cracking open a floppy drive to make an IR filter, but alas.
Yeah, and Chris says that's really cool. And I think we all are amazed that you found a floppy these days.
My tech lead had them in his like filing cabinet next to his desk. And you may ask, is he like my dad's age? No, he's my age. He's like 30. He just still had floppy disks. I don't know why, but we're thankful for it. If nobody else has questions, my slides are at jfrog.com/show notes, by the way, as well as a raffle if you want to try to win a kit to make one of these. That's what that QR code does too. But
all right, let's talk about the 8 queens problem. We start with Genesis chapter 11. The sons and daughters of Adam and Eve began to build a tower to the heavens. And God said, speaking the same language, if this is what they do, they will never strive to do anything beyond their reach. Let us go down and grow their languages, so they will spread across the face of the earth. And many languages were born. A short time later, the sons and daughters of Adam and Eve built a new tower to reach the heavens, and it was good. I'm Aaron David Goldman. I've been working with Python for, I guess, about a decade and a half now. I started doing it with research at Georgia Tech, and then with GTRI, built Python systems for helping to secure a nuclear power plant at Georgia Power. Moved on to Google, where I was building tools that were crawling the internet in Python. Went to 2 startups, ThinAir and T-Cell, both of which relied very heavily on Python for their tools. And now I'm on the Twitter application security team, where we are using Python code in order to read code and try and find developer security bugs before they get into production. So I'm here to talk about the 8 queens problem, and specifically using 2 different languages to try and say the same thing. At first glance, our programming languages seem like they're all the same as each other. Like, we have the Turing church hypothesis that says any programming language can be written in any other programming language. So how can we really get benefits by choosing a programming language, and what are the trade-offs that you should be looking at? So one day I was sitting and just casually reading through Edgar Dijkstra's book about structured programming. You may know Dijkstra from such works as the Dijkstra routing algorithm that all of our GPSs are using to help us find our way. And I ran across this passage where he's talking about a challenge he likes to give new programmers, because there weren't a lot of programmers at this time, and he was trying to decide which of the hardcore mathematicians had what it took to cross the chasm and become a software developer. So he challenges them to write a program that will look at the 64 squares of the chessboard, and challenges them to put down 8 queens on that board such that none of the queens are attacking any of the other queens. Seems like a straightforward enough condition. No 2 queens in the same row, no 2 queens in the same column, and no 2 queens on the same diagonal. So we start down a relatively straightforward procedure. We put down a queen and check if the board is valid, put down another queen, check if the board is valid. If we get to an invalid board, pick up the queen we just put down and advance it by 1. And this way we can just sort of enumerate through all of the possibilities and find the answer. And this would work fine if you had some like robot and physical chessboard, but we need to find a way to represent this in a computer and to solve it. So I'm going to start by giving you my conclusion from the end of the talk and say my experience is that Python is a very powerful programming language for getting things done fast. If I need a solution now, Python's a really strong language, but it tends to suffer in runtime. So if I have something complicated, like enumerating all possible positions of queens on chessboards, I really want that runtime speed that something like Rust can give me. And I'll talk a little bit about why Rust is faster than Python as we're continuing with the talk. So let's start with the representation of the board. I know that I don't need to have a very true representation of a chessboard because I have these constraints and symmetries that I can take advantage of. So I know that no two queens are ever going to be in the same column. That was one of the constraints from Dijkstra's description. So we can simplify our chessboard. Instead of having 64 squares on it, we're just going to represent the 8 columns of the row and say which row in this column has a queen. Every row is going to have at least one. I say 0 is the top row, n-1 is the bottom row. Now I can have a representation in which I show all of my queens, and I don't have to worry about columns overlapping because I've solved a large part of the problem simply by constructing my representation of the board. So we start with pretty simple Python code. I want to be able to print a square so that I can show it to someone. And I say, okay, if it's a queen, I'll print the letter Q. If it's an empty square, I'll just print a space. I want to color it. If anyone here is not familiar with sending colors to the shell, it's actually pretty easy to get colored text output from a Python application. You just print the escape character, seen here as /x1b, which I'm sure is how we all like to think of the escape character at its heart. And then an open bracket, the color, three-number color code that you would like your coloring to be, and then an M to close it. Why the Bourne shell decided that the best way to handle this was to use the brackets of open brace and M, I will never know, but it works fine and lets you get colored output. To print the board, I can just iterate through my board and say, okay, for each square, if this is where the queen is, write your queen. If this square is where empty, go ahead and do the empty. So let's say the same thing in Rust. So the first thing that you notice is minor syntactic changes. So for example, def in Python is fun in Rust. And we need to now have types where we can just say queen and white. In the Python code, we have to be more explicit in the Rust and say, these are Boolean numbers. This is either true or false. The prints basically look the same, slightly different string formatting, but for the most part, it's the same. When I go to print board, I get the first interesting part of the differences here, because my board is an array of integers of length 8 bits, and the number of them that I have is this n as u size. So you're like, as u size. There's definitely nothing like that in Python. U size is the way Rust specifies the size of registers on your system. So all we've done is this simple, let's print off a board, and we are already confronted with, oh, is this a 32-bit architecture machine, or is this a 64-bit architecture machine? And the difference is there. And as I'm casting my 8-bit integer, do I want to turn that into a 32-bit or 64-bit integer for the size of my board and would behave differently? If I, for example, were trying to solve the queen problem for 2 to the 33 queens, this would actually get mad at me if I tried to compile it on a 32-bit machine and be like, whoa, 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 you are overflowing the size of the pointers on your system. So we already see very low-level concepts showing up, but in a relatively forgiving way of just like, okay, this is an array, array sizes are in pointers, pointers are the architecture of your system.
Hi, Aaron.
Yes.
Do you want questions as we go?
Questions as we go would be good.
Why Rust instead of Go, C++, Kotlin, etc.?
So I decided not to do C and C++ because those are not safe languages. And I felt that it was more interesting to keep the safety that Python gives. A lot of what I value about my Python code is that I'm not worried about running buffer overflows. As far as Go, I think that would be a perfectly reasonable thing to go for as a porting for this exercise. And I'm just personally not that interested in Kotlin. I write most of my code for the server, and Kotlin strikes me as the kind of thing for people who like write things for end developers who want things to work on phones and in the wild, and for people who actually want to run code. So now that we have this representation, we can at least print a board and see something that comes up with our fine colored graphics. Like I said, I write back-end code, so this is my idea of high resolution graphics to impress the kids these days. So we'll start with a Pythonic solution. I want to know, does one queen attack another queen? By construction, I've made it so I don't have to worry about two queens being in the same column. Are they in the same row? Super easy. Do the rows equal each other? The diagonals is a little bit trickier, but if you think about the way that I've structured the board, where I have my queens, if I add the row and the column that two queens are in, I will always get a diagonal. Because if I'm moving up the diagonal, I just add one to both the row and the column, and I've gotten to a new diagonal. Or I subtract one from both the row and the column, and I get to a new diagonal. To get the other diagonal, I can just subtract. So one diagonal is as simple as do the sums of row and column add up, and the other one is just the subtraction. This is why I reached for a signed 8-bit integer as a way to solve this. I originally had an unsigned integer, and as soon as I started porting it to Rust, it blew up at me and was like, you're subtracting numbers. This number could go negative. Danger, danger. So that was a helpful place in Rust. Obviously, I don't have to worry about that in my Python code because all integers support negative numbers. Second, I need to check, okay, is my entire board valid? So every time I put down a new queen, I have to decide, is this queen going to ruin the symmetry of my board by attacking another queen? So I take this new attacker queen, compare it to every queen that's on the board, and say, if it attacks, I return false. This is not a valid board. You should pick the queen back up. But if I can get to the end of the for loop without having discovered an attack, then it's a safe queen and I can relieve it. Now, for my actual end queen solving, it's as simple as ranging over the size of the board, checking if in fact I have a valid solution to the board, and then when my solution is valid, check how many columns have I put down yet. If I've already put down 7 columns, or n-1, then I can go ahead and yield my solution and say, I have found one of the ways to solve this problem, and return. If not, I use yield from and recursively call into my function saying, okay, find me more sub-solutions, and some of those will be returned. And when I hit the return, I'm just going to pop back up the stack, having found all of the solutions. Also, my goal here is to talk about the performance of code, so I need a profiler. Now, profiling is a subtle and complicated art. Sometimes you can run across things where you're using more memory, or your computer decides this is a great time to install updates in the background. Maybe you're getting interrupts from the operating system. There's all kinds of things that make benchmarking incredibly difficult. I solved this problem by deciding to, instead of putting a lot of effort into benchmarking, simply benchmark badly. So we are using the tick-tock profiler, which is before you do something, take a timestamp. This is your tick. After you do something, take another timestamp. This is your tock. Subtract the two. That's how much time has passed. It's a really dumb profiler and not particularly scientific, but is good enough for this particular talk because the numbers are not super close and competitive. I don't really need nanosecond precision timing to figure out which of these things is going to be more performant. Then I simply go through, find all of my solutions, and output the number. So let's look at my Pythonic solution. My first thing is I go to port into Rust and notice Rust does not have a concept of yield. So I need to rewrite my code to use normal for loops and not this yield that I relied on. It's a great feature of Python and enables you to write very expressive code. But in this case, I want to write something a little bit simpler, I would say, so that it is easier to port. So instead of having my yield, I'm going to go through, have my two nested for loops where one of them's checking. If I get to the end of my for loop and I have not found a conflict in my queen, then I fall into the else of my for, where I can report that I have found a new solution. But now I've introduced this new concept, which is for else. A lot of Python programmers, when they first see for else, are slightly confused by this construct. The first time I saw it, I assumed that for else was like, oh, sometimes fors never run because the list is empty. So surely else means that it never ran. This is wrong. The actual else in Python should be read as there was no break. So either I am iterating through looking for some solution, or else I hit the end of my for loop without solving my problem, so I need to do the else thing. It is, in my opinion, kind of a wart of Python that this is written as for else. It should probably be like for no break happened, but it's still a powerful feature, and I have found that it is a useful thing in Python. So let's port this into Rust. Now, Rust's for loops don't have a for else like Python's do, but fortunately for us, there is a separate concept in Rust we can take advantage of, and that is labeled continues. So when I get to a point in a for loop where I want to call continue, normally that would jump up to the top of the for loop. But if I get a label, I can say, when you hit this point, continue, but continue all the way up to this new queen rows. So I can jump straight to the outer for loop. And now I can simply put all of the stuff that was in my for else under the code for my for, and I will never reach it if my continue is jumping out of the code. So it looks like we found a way to port the interesting for elseness of Python code into Rust using this jumping logic. So let's look to our friend Dijkstra and say, hey, Dijkstra, can I get a code review on this piece of code? Do you like this way that I've solved porting the for loop? And Dijkstra says what Dijkstra always says, which is goto considered harmful. You should be doing structured programming. You should not be using goto to just jump to some level somewhere else in the code. Because it was Dijkstra's belief that the way to write quality code was to write mathematical proofs of correctness of your code. And if you have these go-tos in your code, anything could sort of jump to anywhere, and that's going to make it difficult for you to write a formal mathematical proof. And we think to ourselves, well, like, who writes a formal mathematical proof about their code? Like, I'm looking at the code, I can see that it's correct, I can run it in my head, I don't need it, and Dijkstra says go-to considered harmful. So we say, okay, let's see what we can do better. So let's talk briefly about structured control flow, which I mentioned earlier. The idea of structured control flow is you don't need the jump instruction. Jump is a powerful instruction that totally belongs in assembly language, but does not belong in the high-level languages that we're trying to actually build systems in today, largely because it makes it much harder to think about the code if you just randomly jump all over everywhere. He derogatorily called this spaghetti code. So we can simplify it by saying, actually, yes, we can implement this logic using nothing more than normal control flow structures, for and if. So we now write it and start with valid equals true. We will assume at the beginning that we have a valid board, go through our for loop. If we find a thing that's broken, we can set valid equal to false, bail out of our for loop, and then go to the true. Now this is actually equivalent to if we had said in our if valid and test. In this way, once valid became false, it would kill all the rest of the loop. So we don't even really need the break, but I'm keeping the break because it gives me slightly better performance characteristics. So now you all know what structured programming is, and you should feel free to use it in your projects. All else is commentary. Go forth and study. You're still welcome to read Dijkstra's structured programming book in your spare time if you are so interested. So now we have a control flow diagram that is based on structured control flow and not this random go-to jumping around. But we still have this problem, which is in our Pythonic solution, we used default arguments. And in Rust, we don't have these named arguments, default arguments to fall back on. But that's easy enough to fix. I can pull out my output, define that first, my queens, and start my timer. So now I'm initializing all my state inside my main loop before I call the function. And we can port this into Python. We can port this from Python into Rust. So at first, it looks pretty straightforward. In Python, we have from time import time. In Rust, we have stood time, use stood time. In Python, we have setrn. In Rust, we have two new interesting concepts. We have const. We are declaring that this n will never change as long as the program is running. I actually like this because not only does it let the compiler produce faster code by being able to assume that n never changes, but it also lets me know that this is never changing. For simply reading the code, it makes my life easier as a developer. As well as I've said I8. This means that my n is only going to be 1 byte in memory. So I did a comparison where I called sys size_of on each of these things. And my n in the Python code had to create an object. It was, I believe, 23 bytes of memory to represent the number 9. Whereas in my Rust, I can use this single byte. This is one of the main places where the Rust is going to get speed ups, is by knowing the types and representing it as less memory, we can get better cache efficiency, and we can just generally torture the CPU less by having less code and smaller data structures that it can iterate through faster. But the main line that I want to focus on the differences here is the actual call to 9 queens. Because if we look at it, we say this is a mutable passing. Now, in fact, what's actually happened here in the Python code is the same thing. I have passed in a list as my queen rows, and I have passed in a list as my output. And each of these things can be mutated by the function. And I have no way of knowing whether the code is mutating that or not. Whereas in the Rust code, I can see clearly that we are in fact mutating this particular object, and I shouldn't trust that it hasn't changed when it comes back to me. Similarly with the output. Output list versus output vector is the same, or setting my thing to a list of zeros versus n as usize. But you'll notice I don't really give enough information to Rust for the types. I say that output is a vector, but I didn't say what it was a vector of. And I say that queen rows is an array, but I didn't say what it's an array of. How does Python actually know the types that are going on here? Everything has to be statically typed. Nothing's going on runtime like the Python. And the answer is it's learning it from the definition of 9 queens that's elsewhere in my program. It knows that 9 queens takes a 8-bit integer as the first parameter, a array, a mutable array as the second one, and a vector of arrays as the third one, and is actually back figuring this up. So even though output and queen rows appear before I pass it into the function is still determining the output. And it can do that because it's got a compile step. Python literally can't do something like that because it has no way to know at the time that I define something, am I passing it into a function or not? It's just doing top-down execution. Similarly for my subtraction, you'll notice I say tick.elapsed rather than subtracting. That is because if you have 2 timestamps and I go to subtract one timestamp from the other, it will get mad at me and be like, oh, you're subtracting one timestamp from another timestamp, but you don't know which one is in the future. You might get a negative time interval, but elapsed time can't ever be negative. That's a type error. So they've actually built this type elapsed And I have to say .unwrap is my way of saying, I understand that it is possible that between the time I took the first timestamp and the time I took the second timestamp, time might have flowed backwards. And in the event that it did, then I'm going to throw an error saying, on my CPU, time moved backwards during this interval. And I'm just saying unwrapped, so I don't care about that. And then my output ends up coming out the same. So let's look at some of the results that I have now that I have completed this porting to Python. So I first just straightforwardly run my Python in Python 3. And it takes about 50 minutes to run this algorithm. And I run my Rust code, and it takes about 10 minutes. In this case, I'm using the 15 queens problem instead of the 8 queens problem, just because making the problem longer demonstrates the differences a little better. But then I realized, oh, in my inexperience with Rust, I've compiled a debug build of Rust. So Rust makes a distinction between, are you building this thing because you're just like in a fast developer loop and you want a really fast build? Or do you actually want to run this code? And I'm like, no, I want to run this code. Let's see what we can do. So now I compile it with rustc-o. Let's optimize this code before running it. And suddenly my runtime drops from 10 minutes to 30 seconds. So now I'm not running 5 times faster than my Python code. I am running, what is this, like 50 minutes versus 30 seconds, 100 times faster than my Python code. So this is now a huge win. But I realized that I'm not being entirely fair because I'm using Python 3. Whereas I know that people who are serious about running their Python fast are supposed to run their Python in PyPy and get all of the power of a JIT. You running an interpreter against a compiler may be a little unfair. Let's see what a proper compiler will do when trying to compile to Python. So then I ran it in PyPy, and it does it in 1 minute and 30 seconds. This is much better than we did using Python, but it's still 3 times longer than my Rust took. As a side note, I also had ported this to Julia, which is a scripting language that writes much more like the way Python does, but really aggressively compiles everything before it starts running using LLVM, which should give me great performance. And while that had a lot of startup time because it had to run this heavyweight compile, it also ended up running the actual TikTok profiled code in just about 40 seconds, only a little bit faster. So let's look at our ultimate results. So I start by graphing on here, how long did it take to run this code in Rust, Julia, JavaScript, Python, and PyPy. And what I found was that I'm getting very different results. The Python 3 is taking many orders of magnitude more time than anything else and totally washing out my graph. You'll notice that these times don't quite match the times from the screenshots. That is because this is a slightly older run and the screenshots were taken on a different machine. So let's look at this in logarithmic space so that we can actually get a sense of what's going on here, since we basically couldn't see anything on the linear scale. And the first thing you notice is that Node has this weird floor. Like, Node never seems to be able to do better than 0.5 millisecond for anything ever. So it's like, okay, what's going on here with JavaScript? And it turns out the answer is Node does its compilation on a background thread. And that 0.5 millisecond is the amount of time it takes for the thread that's running it to take my code and hand it to the compiler thread, and the compiler thread, once it's compiled it, to hand it back to my thread, and my thread to pick it back up again. And just doing this thread interaction is going to take you about 0.5 millisecond. So if you have something you need to run in JavaScript and it needs to run faster than 0.5 millisecond, you've already lost. You can't actually use V8 to solve this problem. The Python 3 at first is doing pretty well compared to things. It's beating the JavaScript and it's beating the PyPy. This is because PyPy, when it hits this function, is actually got to take time to compile the code. Whereas the Python 3 interpreter is not bothering to compile any code. It's just like, give me the bytes, I'm going. And my Rust and Julia are basically not on the scale. It's a little bit misleading because the Julia is doing all of its compilation at the beginning. So because I'm using this TikTok profiler, I'm not actually counting the time it takes to profile my code. So it actually takes about a second for Julia to start up and warm up and get to the point where it's running code at all in the small numbers. But once it tries to actually run the code, it is running it in very short periods of time. But we noticed something interesting around the 9 queens problem. And that is, at this point, all of a sudden, my compilers start beating my interpreter. So Python 3, which was doing pretty well on really tiny problems, is now losing to PyPy because even with the overhead of compiling, it is now being outperformed the CPython code. And the JavaScript is outperforming PyPy because it's got an even more aggressive compiler that's going on, with my Rust and Julia really standing out. They're now something like an order of magnitude ahead. And by the time I get all the way to the 15 queens problem, I've got my compiled code running in less than a minute, whereas my interpreted code is taking over an hour. So if I regularize everything by the Rust code, which was winning my race, I now see that Julia's taking 1.3, but the real cost there is the startup time. Node is taking twice as long to run as my optimized code, but is getting started much faster than, say, the Julia code. My Python 3 takes a little while to warm up. And ultimately, my Python 3 code is taking 172 times longer to actually run things. So my main conclusion is use the right tool for the job. If you're just hacking something together, it's a good idea to start in Python and get something together quickly and running and a proof of concept. But if you really need something that's got a heavy computational load, porting it to something like Rust can really give you a speed up.
Quick question.
Sure.
What about number? The question is, what about number?
I have not tried this with Numba to try and use LLVM to compile the Python. I would be interested to see how it compares.
And I think the follow-up question is, and itertools. But yeah, I didn't finish
itertools doesn't actually help you very much because it's going to be doing a lot more interpretation work. So you're still going to end up in a lot of trouble.
Great. And Monty asked, how would you compare the time if it took to write the code in the different languages? So the people time versus the computer time.
So I would say that the Python was a lot. So I started with just Python and Rust. And writing the Python to get to that first working solution at the beginning of my slides, that took me maybe 10 minutes. Whereas actually porting it to Rust took me about 2.5 hours. Some of that was just I was not as familiar with Rust, so I kept hitting type errors and being like, oh, this thing's actually need to be signed instead of an unsigned int, or this particular thing doesn't match the size of that, so I need to put in an as uint so that I will be able to access things. It definitely slowed me down when I was trying to use the numbers that I was computing to index into arrays, and it's like, oh, I need to actually resize my extend my numbers so that they'll fit in the pointers because the array offsets have to be pointer length. But I think someone who is familiar with Rust would have probably not had quite that many slowdowns. Once I had the Rust version, I was able to port the Rust into Julia and Node.js with very little time because at that point it was pretty straightforward structured programming, and all of these languages support structured programming very well.
Cool, and I think we just, Richard just want to comment, we'll try it. It's only fractionally worse than Julia. So just a suggestion there instead of a question.
Yes, I was impressed with how well the Julia did. That was actually the first person I showed the draft of my slides to, was like, why are you writing things in Rust? Julia compiles super fast. Scientific community loves Julia. You should try Julia. And I was like, okay, I'll try Julia. But for the real problems, it ends up being big differences. And Fortran is the best. Depends on which Fortran you're using. If you're using Fortran 86 with your weird go-to ifs, then no. If you're using Fortran 14, sure. But you are welcome to port this into Fortran and commit it. I'll talk about my GitHub repo in a minute too. So my basic answer is, as you get to very large amounts of solutions, it's going to really make a difference. When you get to, say, 15 queens, you now have something like 2 billion solutions to the problem. And now you start seeing real-time differences that make it worth changing. So here's the surprise, which is, actually, I don't care about the 9 queens problem. This is not an interesting computer science problem to me. I only picked it because this 15 solution set needs about 10 gigs of memory to store. And that's an interesting number for me because that is about the size of the code base that I have to scan. And the fact of the matter is, if I'm running something that takes hours for me to scan it, the code suite that takes 4 hours, I can only run daily. And I end up sending developers these messages that are like, hey, that thing that you pushed to prod yesterday, it has a security bug in it, please fix it. That's not a very great experience for the developer. It's much better if I can get these things to run, say, once a minute. Now, every time a developer puts up a diff, I can be like, oh, I'm going to have a robot comment on your diff and say, hey, we found this bug in your code. Please don't push this to production. We're going to block your merge until you either remove this particular bug that we detected or put some kind of lint suppression warning that says, no, I actually meant to do this thing that looks super unsafe. I said YAML load. What I actually meant was eval any code that was in this YAML file, so it's fine. And we're like, okay, well, you better put YAML load as evaluation on your line. But if I can get it even more performant, one of the big advantages that Rust had, say, over Julia was the 1 second startup time for Julia means it's not a good candidate for being a commit hook. Whereas the Rust code, if I make that my commit hook and it actually runs in, say, less than a second, I can have every time someone tries to commit a change, go ahead and give them that warning. Before they push a diff to the server, before any other developer is reviewing it, before they've lost context of what they're working on, they can just be like, hey, git commit. And it'll be like, hey, you have this particular error. Do you want to do it? And they'll be like, commit message, work in progress. Because now they're actually going to want to fix their things before they make a diff. And ultimately, what we haven't been able to do, but I hope to do, is to connect this thing to VS Code and say, hey, we actually want to respond in real time. Why should I wait for you to save your file to run my tools to find if you have bugs? So here's the one qualified part. Every other part of this conference has just been me speaking on behalf of myself and not Twitter or representing anyone else. But here's my one commercial slide. If you are interested in writing Python code professionally, or you are interested in writing tools of code that read code, then you should come talk to me about the projects that Twitter is working on. We want to be able to solve these problems and to pick the right tool for the job. So we're obviously not going to go and rewrite all of the Python code we have in our systems in Rust. That would be an enormous effort and wouldn't actually gain us that much. But if you can find one kernel of something that really needs that performance, rewriting that in a much faster language is something that you can really benefit from. This is the part where I was planning to stop for questions, but it looks like a lot of the questions have been answered along the way.
Yeah, we don't have any outstanding questions at the moment.
I will give a pitch for the github.com/Aaron Goldman 9 Queens problem. If you have a language that you would like to add, so far I have solutions in Python, Node, Julia, Rust, awk, Clojure, and Java. And I should say that in running this experiment, I've kind of picked on Python 3, but it's not actually the slowest interpreter that I tried. The awk interpreter on the Mac is actually slower than running in Python. So I would recommend you do not port your high performance needing code from Python into awk. I will take a moment to give a shout out for last speaker. I came to this meeting and they pointed me at CodeLab. So it turns out that there is a garbage collection bug in the implementation of awk that exists on the Mac. And it doesn't always clean up the garbage, which meant I couldn't test the 15 Queens problem because I ran out of memory on my computer. But using Colab, which was pitched at this last meeting, I was able to both implement my Python and run it and get nice timing because Colab supports all of the shell text coloring, and was even able to run the awk version on Google's Linux servers with basically the same structure to be able to get my timing numbers for awk. So Colab is great if you need a Linux environment, but you're on a not Linux machine. I do recommend letting Google servers be your Linux machine for you, even if you just are like, hey, this shell should totally just be a bash file on Google's computer. Please don't do anything evil by smuggling yourself as Google. All right, any questions, comments, concerns?
Hey, this is Jeff. Or was there someone else? Or
No, go ahead, Jeff. Good.
okay, because I don't think I can actually add to the Q&A, so I got to do it real live. So for your code analysis tools, what language do you write those in?
So the vast majority of it is currently in Python. We do call out to some C libraries that we got wholesale that can do scanners. There's a bunch of good like Valgrind type things that you don't necessarily want to write yourself if you've got some analysis tool that can find that memory is leaking. As well as we use that to be able to call Rust from Python. So even a lot of the Rust things that we are trying to do now that are a little intensive are likely to be called from Python. But the hope is to create a binary that can actually work as a commit hook that we can just push out to every developer's machine.
Cool. Thanks.
Richard wants to point out, hey, great group, Twitter security, by the way. They were the first to talk about HTTPS to OWASP. By the way, Richard, if you want to try to get the mic, we can try to get that to you as well. Anybody else who wants a mic, I can try to pass it to you if you'll raise your hand.
I'll definitely say we strongly support the use of HTTPS. Oh yeah, if you want to commit a Fortran version to this repo, like pull requests welcome. I will totally take your Fortran code. Again, as long as it's not Fortran 68, which is terrible. Only Fortrans from like the 80s.
72
plus.
Or so.
Yeah, I'll probably take 72. I actually never used Fortran 72.
Anybody else want to raise their hand? Anybody else have questions you want to ask directly?
Also, the link to the GitHub repo and slides are in the Hangout.
And if you want to also put those in chat, that would be great. People will see them there before they go.
Okay.
I have a quick observation. You may want to try like the homebrew version of awk, like which is pulls from a more up-to-date resource. Like many things on the Mac, the default packages may be many years out of date, and there's a more up-to-date version that you could pull in and try to run and see if that performance is different at all.
Yes, the homebrew awk performed better than the default Mac awk. I was very surprised when I found a bug in the awk that comes with Macintosh. I was just like, what? Surely this is not an operating system bug that I've just stumbled across, but like, okay, fine. Like, I'll install real awk.
There's, yeah, the default packages that come with the Mac are pinned and not awesome, and for any junior developers out there who are on a Mac, at least, Homebrew is your friend to get modern, updated versions of pretty much everything that you need.
Yeah, my working theory is that they forked the packages when they set up NextOS, and they just haven't updated them since NextOS was founded.
Yeah.
But the Objective-C support is good, so there's that.